Hey guys, welcome to the first installment of Chapter 3, which is on projectile motion. The chapter starts off in your book with it starts off with vectors and scalars, which I already have a video on, the reason I didn't hold off on that video until now is because vectors and scalars were kind of important to know in Chapter 2. So I started off with vectors and scalars, but now, which is nice that now we start in the middle of Chapter 3 at around 3.4, which is projectile motion. Okay, so projectile motion, what's a projectile? It starts off at 3.4 defining a projectile, kind of. So projectile is really any object in motion. It's like a body in motion, basically. Body in motion. I bet that before your physics classes, you've always thought of a projectile as maybe like a bullet shot from a gun, which is true. A bullet shot from a gun is a projectile, but other things that people don't think of as projectiles are satellites. You know, in our atmosphere, those are projectiles. So now we're going to talk about a little bit about the nature of the movement of these projectiles. So I'm going to start off with kind of drawing a rough sketch here. See if I can get it decent looking. You also have this in your book, so if it's not too good, then take a look at that one. So it's kind of a platform. Think of this as a table, okay? Oh, my phone, okay. Sorry, I'm making these videos consecutively, so in the last couple there's been some rings of my phone, but it's beside the point. You have a ball here, and you can see this, and you can see this on your book, in your book, and you have a ball here on the table, and it's rolling, okay? And it looks like someone has rolled the ball on the table, and as they talk about this diagram, they mention when you're talking about projectile motion, always look at the vertical component separate from the horizontal component. So this diagram here is basically dissecting the horizontal component. So horizontal meaning these directions, not up and down, side to side, right? So always look at, so this is the horizontal component, and it was rolled, yes, it was rolled by maybe a hand, so that was the initial force. But since there's no other force acting on it, we're talking about no friction, which is unrealistic, but no friction, okay? No friction. This is just gonna, its acceleration is 0. Its velocity is moving, it's not changing. It doesn't change velocity because the friction is 0, okay? So that's what you have to realize. So when you have a horizontal component of a projectile, you have to know that when there's no horizontal force acting on it, the distance between each interval will have the exact same distance. It won't change. It won't increasingly get greater and greater and greater. See how these are all constant? Because the acceleration is 0 meters per second squared. Now the velocity could be something else. The velocity could be whatever it was rolled at. Like if it's a bowling ball and I rolled it on the alley, then I would roll it pretty hard, it would be going fast, but if there's 0 friction, then it wouldn't accelerate. And each passing second, it wouldn't increase in speed, which is what this diagram is showing. So basically, what you need to know about this right here is that horizontally, oops, I just moved my screen here. There we go. Horizontally, projectiles only change v with a force, okay? So, and you can think of when it changes velocity, it's going to change acceleration also. And when it changes acceleration, change delta, when it changes acceleration, that inevitably leads to increase in the interval between each. So each passing second, maybe, okay, one time it's here, next time it's here, next second it's here, but then if it's accelerating, the next second it's going to be here, and the next second it's going to be here, and it's going to keep, the intervals can keep getting larger and larger and larger because it's accelerating. But with this, you have to know, right here, with no friction, there's no acceleration or deceleration because there's no outside force. So now we're going to dissect the vertical component, which is, I think, more interesting, but it is harder to grasp. So now the vertical component of projectile motion, we go back to chapter 2 and we think of free fall. Free fall balls accelerate, or objects accelerate while moving down. So let's say we have this red ball here, and and this is, let's say, 0 seconds. Then in 1 second it's here, but then a second later at 2 seconds it's here, and then at 3 seconds it's down here, and then let's say at 4 seconds it's at rest down here. Okay, now why is that? This is because of acceleration, right? Acceleration. Okay, so when you have when we go back to the table example, the horizontal component of motion, on the horizontal component of motion, sorry, I can't talk today. On the horizontal component of motion, each of these intervals was the same. It never increased in distance because the acceleration was 0 meters per second. But that was horizontally. Here, we're in free fall, we're falling downwards, so our physics knowledge tells us that the acceleration is 9.8 meters per second squared, because that's the gravitational acceleration. And there's no friction, of course, because we're dealing with free fall. So each passing second, the distance interval will get a little bit bigger. And we can determine that with the equation d equals 1/2 gt squared, or d equals 5t squared, basically the same thing, right? That we dissected this equation a little bit in chapter 2, right, when we were talking about free fall. So that's where this comes into play. So when you have, then, now that we have a basic understanding of the vertical component, up and down, acceleration is 9.8 with no other force but gravity. And then one thing you have to notice is with horizontal components, with the horizontal component going this way, gravity doesn't affect it horizontally. It just doesn't. No g, okay? I mean, obviously gravity is keeping it on the ground, but gravity is not affecting it. So with no friction, there's no acceleration, there's no change in velocity, no change in v horizontally, right? Horizontally. But there is a change in v vertically, which is what we saw here, okay? You can think of each passing time interval getting bigger and bigger and bigger. You can think of that as a change in velocity, okay? Or speed, because our speed equation, of course, or our distance, or velocity equation is speed equals distance over time. So that's how that factors in there. So now I'm going to dissect a bit, kind of a diagram here that I snagged off the internet, just to kind of give a little demo of it. So this is the diagram that I got. It's pretty nice for, it's computer generated, pretty nice for displaying the basic concepts. So here we have the same ball, okay? The ball starts from the same spot up here, as you can see. Actually, I'm sorry, let me switch to my drawing utensil here. The ball starts at the same spot, right up here, okay? That's not the best color. And then let's say it's launched, it has a force. It has a horizontal force, so it's launched downwards like this, okay? It's launched in this path, okay? Now, since it's in this path, we know that there's both a horizontal component, oh, sorry about this. There's both a horizontal component and a vertical component. But after this initial force up here, after this initial force, there's no more horizontal force. No H, sorry about that. No H force, okay? That's an H. No H force, okay? But there is a vertical force, which is G, gravity. 9.8 meters per second squared, okay? So you have to know, so if you see vertically, this component's not changing. I mean, sorry, horizontally, this component's not changing. It's going the same horizontal distance constantly, always horizontally. But vertically, it's increasing, right? It's going further and further and further down with each fall, which is because it's accelerating at 9.8 meters per second squared. This is the parabolic path with a combination of horizontal and vertical motion, okay? So the horizontal component is completely constant. H constant. No external force, right? But downward, vertical V, vertical is accelerating, right? At 9.8 meters per second squared. So the result is a ball that increases in vertical distance each second but remains constant in horizontal distance each second. And that is a basic introduction to parabolic projectile motion. Also, just a quick note here, you'll see the vertical here and the horizontal components separate. So vertical, as you can see, it's increasing each second. The distance is increasing because you have that 9.8 meters per second squared. But here, you don't have any acceleration. You don't have an external horizontal force because gravity doesn't act horizontally. So each interval is constant, and that is the basic principle of parabolic projectile motion. I'll see you in the next video.